Hi, my name's Duncan. Welcome to one of my hot takes. This hot take is about cracked curved branches, which have also been called hazard beams by some people. So let's get going. Briefly, let's look at what causes curved branches to shear crack, as shown on the image on this slide. If a curved branch is bent in a direction such that the force applied will cause the curve to straighten out, then this may cause the branch to split longitudinally, a shear crack. This is most common on branches that curve upwards, and the combination of static and dynamic loading at some point is strong enough to crack the branch at this curve by bending it downwards. The strength being challenged here by the curved branch being straightened out is the tangential tensile strength of the wood, which is much lower when compared to the compressive or tensile strength of the wood of the branch along the branch's axis under normal bending scenario. Experimental sources suggest that difference in strength is between 5 to 20 times. So that wood is 5, it needs a lot less force to split it apart. I would note that it requires a particular movement to occur for this to happen to a curved branch, and the curve typically needs to be quite abrupt in the form of the branch too, which is why this happens to a reasonable extent in a number of species, but not endlessly to all curved branches. I would also point out the same kind of shear failure can occur in curved or dogleg tree stems too, so it's not just to branches. Professor Dr. Klaus Mattock called these features hazard beams and claimed that because the crack was situated in the center of the bending forces that are acting on the branch, the tree could not itself detect this fault, and thus a branch cracked in this way could never be repaired. This suggestion was not substantiated. Later work by Professor Enos, published by the Royal Society Proceedings B, clarified the equation for bending forces upon juvenile branches with a logical explanation as to why these curved branches are prone to cracking in this way. The Proceedings paper also explains why the longitudinal crack terminates as the weight of the branches acts to pinch together both ends of the crack as the curve progressively straightens out. Mostly, the cracks that appear cease to extend after running through the whole of the curved part of the branch. One exception is where the crack may not propagate that far because a large knot is positioned in the middle of the curved section of the branch, and that knot can prevent the crack from propagating to its full extent. Dr. Lonsdale, from multiple observations, has written that some of these such curved cracked branches fail later on, in perhaps another wind event, at the distal and often at the distal end of the cracked section of the branch by twisting and then often drooping down, particularly more juvenile branches, or just twisting and falling away at the distal end, which is more common in larger diameter branches. I personally have also observed this effect of a torsional failure for these cracked curved branches many times, mostly in oak and willow trees. There's also the possibility that wood decay, initiated when the crack opens, may develop such that the branch fails because of this secondary decay. In my experience, this is more common in larger diameter branches of decay-prone species. Okay, hopefully this has set up enough context from that last slide, set up enough context so we can do the hot take part of this, which is essentially me complaining about how things are at the moment. So really there are two issues here that I would like to raise in relation to this. First, that the term hazard beam is just wholly inappropriate to describe this feature. And second, that these cracked curved branches have mixed outcomes. Their failure as individual features is not inevitable, and further scientific work could be beneficial in assessing them for their associated risks or finding their factor of safety at different stages of their development. So first, the word hazard beam. The term hazard beam. Well, hazard beam is just two words. To my mind, both of these words are very poorly chosen. Science has not yet shown that cracked curved branches all present a significant hazard to targets. By observation, it's clear that some twist off or continue to the point where they have full failure, as Dr. Lonsdale observed. I can't deny I've seen that too. But others recover and persist in the tree after wound wood does form around the initial crack. The use of hazard for just this feature is also inconsistent in how we report about component parts of trees. If a stem has decay at its base, we do not call it a hazard stem. If roots are severed on a tree, we don't call them hazard roots. There's too much assumption here in using the word hazard to describe a very specific component part of a tree with a very specific supposed defect. The use of the word beam is also inconsistent for our language that we use to describe trees. In no other situation, when describing trees or tree parts, do we call any component part of the tree a beam. Not the stem, not the roots, and even a branch that is curved but hasn't cracked, no one would describe that as a beam. Overall, the term hazard beam will never translate well to lay people. That's a litmus test for me. It's far better to report these features as cracked branches or cracked curved branches. Personally, I prefer the latter because it's fully descriptive of what you can see. In the USA, they don't call them hazard beams, they're called shear cracked branches, which is a little technical but still conveys what they are sufficiently. If we want to understand if this feature, this cracked curved branch, has a lowered factor of safety, then more science needs to be done. As Professor Enos explained, the crack is unlikely to extend due to the weight and leverage of the branch squeezing both tips of the crack. A cohort study or a series of mechanical experiments may help to identify what forces are needed to cause failure and could help corroborate Dr. Lonsdale's observations that some fail in torsion, probably with some bending too, to be honest, after the initial cracking. There's also the factor of wood decay to potentially help to explain differing outcomes. So there is no doubt that some of these cracked curved branches can be unstable, but others persist for decades, and wound wood can act to strengthen them further, an observation easily made which Mattock's writings omitted. The image on this slide shows one of the figures from the paper by Professor Enos and Adam van Kasteren, which considered various ways in which juvenile branches can mechanically fail. I'm just going to read out the image caption from the paper so you get a full explanation of what this image is showing. So the title is Patterns of Bending Failure Predicted for Branches. An initially curved branch, A, should split longitudinally down the center line if it is subjected to a force tending to straighten out the curve. By contrast, an initial straight branch made of low-density wood, such as willow, B, should buckle transversely inwards, its section flattening out when bent. A straight cylindrical branch of a reasonably dense wood, C, should break halfway before splitting along its length at its midpoint, what's known as a green stick fracture, while a well-tapered branch, D, should break halfway across, then split distally. Okay, so what have we learnt? First, we should not be calling these features hazard beams, as in individual cases we do not know that they do present a significant hazard. And why has a branch suddenly become a beam just because part of it has cracked? It's nonsensical, and most importantly, it fails to communicate the issue to others. Second, Professor Enos has provided useful biomechanical equations that explain the influence of the factors that lead to this curved branches to crack in relation to the lower tangential tensile strength of wood and the extent of curvature alongside the force applied to straighten out the curve. This is rigorous science upon which one could build. Third, it would be useful, I think, in arboriculture to have a cohort study or carry out mechanical testing, maybe both. Although the mechanical testing would need multiple specimens and because you'd have to test it in different ways. But this could be used to determine what loss of factor of safety these cracked curved branches represent. If we are going to do the mechanical testing, testing specimens at different stages of wound wood development would be really helpful, as well as looking for other factors that might explain why some fail and why others persist. The image on this slide shows a cracked curved branch in a mature oak tree where significant woundwood has developed along the crack. These features can be microhabitats for bats and other wildlife. If we could be confident a specific cracked branch is likely to persist, it may provide benefits to retain it, then rather than doing blanket removals of all these features in all species of tree. Overall, my message is this: do not call these features hazards by default until we know for certain that they all are, which seems unlikely given the tree's ability to repair cracks with woundwood. Thanks for listening to my hot take. Talk again soon.